force can act on it, and so your acceleration could be a function of displacement. Yeah. And acceleration could also be affected by the friction. Now, friction is proportional in the linear case to speed, right? So this could be a and what else? You have a motor. You have an input force. Something you can manipulate, something you can change to get what you want. Right? In order for this thing to move as prescribed, you have to be able to affect the motion, right? You have to be able to change it. Change what? Change the acceleration. By what? By doing what? By applying force to it. Yeah? How do you apply a force to an object? By using something like a motor. Right? Does that make sense? Yeah. We're talking clear, distinct causality. Causality. What causes the motion? What makes this thing move? How does the all these parameters affect the motion? How do you describe it? You describe it like this. But we're not done yet. Yeah. What else? We could have somebody else, or this is connected to something pushing back to it, yeah. Right? And that could be external, in addition to the friction, right? So it could be a force, external force. External meaning it applies to the object, yeah, for external sources. Right? And contrary to what you were told in linear system, where you assume the system is not only linear, it's time environment, right? Time environment, remember that word? Yes. What does it mean? What does it mean in the time environment? Well, this whole relationship changes over time. Changes over time. 1 minute this way, the other minute is different way. Like the airplane flying, right? A few years ago, Andre, your local student, may have the memory of an airplane crash close to Buffalo. There was an airplane flying at night, and in the course of flying, the ice accumulated on the wings. And that changes entire dynamics, changing this dramatically. And the pilot was trained to handle it, but pilot made mistakes. People make mistakes. The point is, the automatic control system wasn't able to handle it. It wasn't able to handle it 50 years ago, like Chen pointed out in his paper, in his book. It cannot be handled today. Properly, automatically. Okay, so you see, this is what you are describing is a mathematical description of how this motion works, and it comes down to not position displacement, not acceleration, but the acceleration, not the speed, but the acceleration. The highest derivative in the system tells you the whole story. Okay? So you are not controlling anything. Okay? You are affecting, you are regulating, you are tuning, you are guiding it toward what you want, okay? Where you want to go. Okay, you take on the bus. Yeah? The bus driver drives to the next station. Yeah? The bus driver cannot move the bus immediately to the next station. Right? The bus driver pushes it down on the gas pedal and moves, and then use steering wheel to guide the bus to the next station. Right? So you cannot say the bus driver control it. The bus driver can control the gas pedal and control the steering wheel, but it can only he or she can only guide the bus towards where you want to go. Same thing with control system. Same thing with what we call control system. But we never made it clear. We never made it clear. When we guide, in this case, when we guide the displacement toward where we want it to be, we do not have absolute authority to just change it instantaneously. We do have the control over what this motor does, right? That's when we let the ball, we can turn it on, we can turn it off. Then we can call that we have control over that. So from the very beginning, there were a lot of inaccuracies of how we even describe what we're doing. And that causes the problem down the line. Right? So this is the in general, the mathematical, even though we didn't write down what this function is. Yeah? But this is in general what we are trying to describe. Okay? But then all of a sudden, it jumped out of nowhere. In the blue, we have a classical control theory or classical control error. We say we have a transfer function. Right? Our entire the full semester course is devoted to control the transfer function. Yeah? And then we have order control. Yeah? Order control, we assume you're given a problem like this. Again, you input U, output Y. But let's create a twist. You mentioned the state space. What is the state space representation do we use to describe a dynamic system? What is the state space representation?
The matrix AX plus BU.
AX plus BU. Yeah. Very nice. You know what you're talking about. Yeah. But that's the equation that describes how U changes the state vector. It's actually the vector, right? So it's a matrix of first order differential equation. It's still differential equation, but it's the matrix of first order differential equation. What is Y?
CX plus DQ.
You know I kept the place for it. So all of a sudden we were given this. And linear time environment, LTI. But did anybody explain to you how do you go from here to there? This is the physical reality. This is what's studied in the textbook on paper. Yeah? What do you have to do to make a connection? To go from this is something moves, something goes around. Okay? But what sequence of actions, and more importantly, what assumptions we have to make to get there? Because once we get there, you took control theory, you took linear system theory, you took all those tests. You know what to do with it, right? But my contention has always been knowing what to do with it. is important. But it's only a part of the story. Right? What you learn in control theory, in classical control theory, and in modern control theory, I wouldn't call it control theory. I would call it mathematical foundation for control theory. Because just knowing all this cannot directly help with this. This is why people out there every day tuning PIDs, left and right. They don't care what theory they learn in school. KP, KI, KD, up and down, left and right. No connection. There's no connection. So I'm here to help you make the connection. If I would tell you that by the end of this class, by the end of not today, by the end of this semester, and you can take a physical problem, you can use all you learn, and you find a solution. Not the solution of a math problem, as taught in classical control, as taught in linear system, but solution to the real problem. Making it go where you want to go, in the measure you want to go, respecting the constraints, physical constraints, respecting the industry standard. Yeah? That's what we're talking about. So let me help you. Let me begin by helping you filling in the blanks. How do you go from here to here? Well, you have to make this assumption. You have to make the assumption that the relationship is linear. This is not a linear system, right? And you have to make assumption. The disturbance is out. We don't even see it, right? You have to assuming that this never changes. Right? That's what makes this a mathematical problem, a good one. An important mathematical problem, but a mathematical problem nonetheless. Right? Now, can anybody help me go from here to a transfer function? What is the transfer function given this differential equation?
Output by input.
Was that output
By input.
Output by input like this?
Yes.
But I have a white out here. I have a white out here. How do I do this? We go to the frequency domain. How do I go to the frequency domain?
Laplace.
It's the Laplace transform. So I take the Laplace transform of both sides, and this is not just this is not ratio in time. This is ratio in frequency, right? Right? And ratio in frequency. I will let you figure out the details. I'll let you figure out the details. And this goes here. Right? So how many assumptions do we have to make? We make assumption system linear, which is never true. We make an assumption there is no disturbance, that's never true. We make assumption that never changes, that's never true. Okay? So we are solving a problem that doesn't exist. We're solving a mathematical problem. And maybe we can use what we learned here to solve a real problem, but don't pretend that we have a real problem solved. This is why we have so many engineers out there who have no idea how to tune a PID other than trial and error, other than some experiential formula. We have one paper published, the most famous paper published on PID tuning. 1943, Livers and Nichols. They gave a table for PID tuning, but nobody ever explained why. That is completely unacceptable, right? If somebody tell you, do this, just trust me, do this. Would you accept that? In $1 million chemical plant, just do it. Right? So the disconnection looms large in the background for the last 50 years, 60 years. Okay? The professor keep teaching this, left and right. They pretend this is the real problem. They pretend they're teaching control. In reality, they're teaching mathematics. This is what Gunter Stein was talking about. Worshipping mathematics. Because if it's mathematics, gee, great. That's very powerful. Right? Once we put in the mathematical symbols, it has to be true. Can somebody tell me how to come up with the A and B and C's based on this? The state-space model, A, B, C, D. Anybody? There's more than one solution, but what's the easiest one to come up with?
You need to perform a variable substitution.
If you've done your linear system right, just give me this. Then 2 by 2, 2 by 1, 1 by 2, 1 by 1. You know, right? You know, right? Final exam or first quiz or somewhere in between. You know the answer, right? Does it sound familiar?
Right.
Yes? If I make a mistake, you will tell me, I'll give you a lecture phone. Right? But it all come from the differential equation. If you got x1 equals y, x2 equals y dot, and go from there. Okay? So x dot equals x1 dot, x2 dot, and you from this equation you right? So that brings us to here. What assumption did we make? Again, linear, right? This is linear, no disturbance, time invariant. The same assumption we made here, but why all of a sudden we create another set of another layer of mathematics? Because mathematicians in late 50s, early 60s said, you guys don't know anything. Okay? If you do what you do, you're never a scientist. You're just a technician. Okay? Because if you look at what the classical design, what the core was most authentic material, most important, most significant methodology in classical control. You will see this. So classical control call it G versus call it U. R, this is Y, this is E, right? That's how classical control frame the problem of control. The classical control frame problem as well is feedback. Some familiar feedback control. You're feeding this back, and you're adding this called a controller or compensator. Okay? And you design the controller, whether a PID or just a transfer function, to meet your design specification, right? So what's the most valuable lesson you learn from classical control? What is the most important concept or design principles that you take away from 440? In our curriculum, it's EEC640, right? Gianfranco?
That's right, yes.
You took that, right?
Years ago, yeah.
Years ago, and Andre?
That's right, yeah.
Yeah? Matt, you remember that? No, Matt didn't take it here.
No, I did take the class here.
You did take it from here. Yeah. Okay, so now you're on the book. Okay, what did you learn from it? Years later. Years later. Anybody else from other schools, from other countries? What still? Does anything come back, or emptiness? Nothing.
Closed loop and open loop.
Yeah. What I put up here? This is called open loop, right? There's no feedback.
No feedback.
And this is a closed loop.
Yes.
But just that's an empty concept. Doesn't mean anything by itself, right? What does it matter if I call it open loop or just plug? There's no loop, right? Open loop means there's no loop, right? Right? If you think about it, nothing makes sense. If it's open, why we call it loop? Right? There's so many things you can pick up. On. If you just think about it on your own, if you don't take everything for granted, you say, why do you call this?
No feedback.
No feedback. But I challenge you. People say, what do you mean there's no feedback? There is feedback in here. That if you make it too fast, the natural friction will eventually cancel out your motor force, and your other go any further, any faster. So you say there's no feedback. There is internal feedback. So feedback doesn't explain that at all. So the concept of feedback doesn't explain. Concept of feedback comes from communication. I'll talk about it later. They borrow this from somewhere else to say, oh, there's a feedback. And this is the most important concept in control, where it's already in here. And later on, I'm going to show you a great Chinese invention where they built the feedback inside the physical layer. There's no separate feedback. You don't just do this and then do feedback. You can build this into it if you are a great engineer. You don't have to rely on what you do afterwards. You see X29, why it had to retire? Because no amount of fixing after it was built, no amount of fixing can fix it. So if the aircraft design people have any ideas of real feedback, of something built in, they wouldn't have that problem. They wouldn't. So once again, what did you actually learn from it?
Stability.
Stability, another concept. I'm not talking about concept, they just throw concept left and right.
Professor.
What can you really do? What can you do otherwise, you wouldn't be able to do without, learning, without taking 440?
Like, depending on the goal, like a positive and negative feedbacks when it needs to be given.
Let me give you some history.
So is it model predictive control?
Come on. No, that's not even in 440, that's not quite the level. No, I think it'd be very hard for you to actually get to where I'm going at. I lost my train of thought.
What I recall from that class and that diagram you put up there is that the circular dependency,
Right.
current state of Y
Right.
affects the next state of Y, and the difference between Y and R being the error.
Right. So what this describes the causality. This is the cause, this is the effect. Okay? But what actually transpired in the so-called closing the loop, in so-called feedback control, these are all concepts. But at the bottom of all this is the restructuring of causality. What do you mean by restructuring? It used to be just one way, right? This is cause, this is effect. What happened here? This is still a cause. But this no longer just effect, because this common back through this so-called compensator controller changes the cause. So now you have a what Matt got from the other class, unfair advantage, right? From another class called circular causality. Circular causality. So it's no longer just a one shot, one time deal. It's what you do will have a consequence. What consequently comes back will affect what you do. That makes sense. That's psychology, right? Psychology right there. You have a purpose. You want to graduate with an A, right? So you work for it, but when you didn't get A in the first assignment, so you come back and you say, oh, I'm going to work harder next time. Circular causality. But you never heard that, right? You never heard that. They never teach you the essence of what is being done. Being done. You know, what is the greatness of James Watt's invention of flyable governor controlled imaging? Well, he didn't invent flyable governor. Flyable governor was taken. Daniel, what's his name? In the other class, did the investigation. Another student from another class. James Watt never invented flyable governor. He took it from somewhere else. Huh? But he used it to what end? He used it to change the speed engine engine speed regulation from open one linear causality to circular causality. The engine speed will come back to change the steam wall, right? Therefore, he was able to regulate engine speed to great effect. Still not perfect, but to great effect. So much so, it caused the first industrial revolution. It's not perfect, but still, it's good enough to change the human history. And today, we studied it in our textbook. It's the most primitive control system, right? It's a proportional gain. So what is the greatness of Jim Watt? For the first time on massive scale, he introduced circular causality to industrial process. That's what he did. That was his greatness. And the mathematicians had a hard time elevating from his invention. They couldn't figure out what's the basic operating principle behind his invention. They can perfectly state Newton's principle of motion. But they have not been able, even to this day, I haven't seen a satisfactory explanation of James Watt's invention. They have a big collection bin, and they call it feedback. Okay, every time they couldn't understand it, they just, oh, this is feedback. Assuming you know what that means. Okay. So what exactly is the breakthrough here? There was a breakthrough, you know, in the Second World War. Something happened. There was a group called servo engineers, MIT people. There were a group called communication engineers, Bell Lab people. Right? During the war, the two groups came together at MIT to design the anti-aircraft gun control system to automatically shoot down the aircraft. They did it to great effect. At the beginning of the war, they were able to shoot down 2% of German aircraft or cruise missiles. But at the end of the war, 97%, 98%. That one war for them. And they took Air Force, took the air power out of the hands of the Nazis. Right? And if you notice what happened in Ukraine today, right? The balance shifted when the Ukraine military got the missiles that took down the Russian aircraft. Russian can no longer rely on the air dominance, and that was the beginning of the shift. And so airport were very important, obviously. But what has that to do with this? This changed it. This made it possible. How? How did this make the aircraft defense system go from 2% effective to 98%? So if you do not know history, you do not know what you're studying. You do not know what you're doing. And unfortunately, that's how it's being passed down generation from generation. You hide behind the concept feedback. Feedback is so great. The single most important concept in modern history. Let's study it. What is feedback? Feedback is what? Everything we don't understand, we call it feedback. Open loop or closed loop, great. Closed loop is much better than open loop. Like we're in kindergarten. This is not ideology. There has to be a rationale. So what was the rationale behind the success of anti-aircraft gun system or breakthrough in anti-aircraft fire control? The success began with the guy who designed the servos. They realized that the bottleneck has been bothered them for decades. All of a sudden, that bottleneck is gone. It used to be, but they can design servo system on a ship, The ship steering, that's servo, right? That's where the name came from. But for the aircraft gun control, it's different from the ship gun control. Is aircraft fly very fast. You only have 15 seconds to move your gun. 15 seconds is a long time. 15 seconds, very short time for the ship. Ship moves slowly, so on the military ship, the gun, the servo is more than enough. But when they try to adapt it to the anti-aircraft, it's crazy. They try to make it fast, the thing vibrates. Quickly it reaches limit, and that's what Gunter Stein was talking about. Because available bandwidth is not enough. But of course they didn't understand it. So they reached a hard limit that they couldn't break through. To the point the gun can be fast enough to target, to point to the aircraft. But the breakthrough came when the servo guy realized that they have a theory. They have theory to rely on to make this thing, to make the bandwidth or to make the system much faster than they wouldn't be. They would otherwise be able to do. So what is that theory? What is the theory that you learn in 440 in control theory that allows you to greatly increase the bandwidth of your system, of your closed loop system? Or at least to understand some of the major stability. What is the reason for instability? How do you make the system so that you have a lot of room for variations, parameter variations, and until you reach the envelope and reach instability. So the fact was, they reached before the breakthrough, the servo engineer designed their system. They put it faster and faster, and quickly they reached the ceiling. They couldn't go further. Right? And then they learned something that you all learn in your 440. Oh, this is what caused instability. Let's fix it. So what is that? What is that in 440 that allows you to say, oh, no brainer. I need to do this and that to avoid instability. So stability is no longer a guessing game. Stability is clearly understood. Once it's clearly understood, it can be achieved with high efficiency and higher bandwidth. So it's all about understanding. There's something in 440 that once you understand it, okay, you can make this as fast as you want, at least mathematically. So what is it? If you could not answer the question, you are not alone. You are like everybody else out there. They took 440 and they never understood it.
If I was to wager a guess, and again, my understanding is very low as you're describing, I think what could help them is loop shaping. So
Loop shaping is you're getting close. Loop shaping is the design method. But what enables loop shaping? So go further, go one step further to the most basic understanding of this. The out of that comes loop shaping design.
Are you talking about either the Bodhi plot or the root locus plot?
Right. Well, macros for Bodhi or root locus. Take your kid. They're distinctly different. I want you to be able to see their differences. Because they were taught in textbook, just like parallel. Root locus Rules Gervers, right? Bodie and Nyquist, go study more.
My reason for saying that was with how I understand it, loop shaping, you can desire the frequencies that you want, you can identify the frequencies that you want to use where your machines will be most effective. And then use that to disregard signals that are either too high or too low.
Okay, that's enough.
Okay. I'll just.
Not to demean, but let me tell you the story that will allow you to come to the conclusion yourself. Right? Remember the remember this. Right? Just well left. I can turn this on. Right? Op-amp. Right? The predecessor of op-amp. Right? And he invented it. He such a big invention, he became a godlike for a figure. Right? But he had no idea. You know, sometimes it works, sometimes it doesn't work. And what problem did he solve? Well, a mu is the amplifier again, very large. But the problem is the S in, S out. This is all about the signal, right? You amplify signal. Right? S out or S in. If no feedback, it's just mu. Right? But the mu is build a multi-stage vacuum amplifier. Vacuum amplifier or nonlinear. Nonlinearity introduces distortion, and quickly your voice becomes unintelligible after you put in a few more of these. But that was the problem of the telephone industry. The solution of that problem helped the gun industry. Okay, the power of mathematics, power of understanding. So okay. I wouldn't tell you where I get this equation. You should be able to know, right? So you make the input output again, not a function of mu. That's black solution. Not function of mu. Mu and beta is much larger than 1. And this is approximately mu beta, right? This is no-brainer, right? Yeah, so black solved the distortion problem. But problem is when he loop it back, sometimes it's stable, sometimes not stable. Nobody understood why until you mentioned not rule locus, not rule servers, a hero of modern age. Right? We put them in parallel. They're not parallel. They're not even close. I can completely forget rule servers. That's useless. I can completely not teach him rule locus in 440. You never use it. But I cannot do without body plot and negative plot. I cannot do it. Nobody can. Right? So the instability problem was finally understood or solved by 1932. Harold Nyquist. Right? And 1940, I don't remember, by Henry Bodie. these are the heroes, these are math heroes. Their mathematical analysis allow Bell Labs to do this systematically, to avoid instability. Yeah? And they were minding their own business until the war came. Then the civil engineer came on this. This is great. This can be used to analyze stability of a gun control system. Okay? So this is class of control, and the loop gain, the mat. I'm sorry to shut it down, right? But the loop shaping he is talking about is this C of J omega, G of J omega. Okay? And it's 0 dB. Okay? And you need to make, this is called loop gain. Because you go around, this C could be in here, the answer is still the same. Okay? You go around loop, and you multiply the gain. You call loop gain. Okay? For this thing to be stable, the loop gain must have this shape. It's a 0 dB crossover omega C. Because 1940 they figured out that if the gain looked like this, the phase angle will look like this. And this is phase margin. I'm sorry. This is phase margin. How far it's away from minus 180. Okay? Phase margin. So not only they Nyquist derived the stability condition, Bode gave us the idea of a phase margin. Okay? And they were able to stabilize this and that. So that's an outstanding engineering achievement in the world. But listen to this. This is not neither. There's no transfer function. There's no transfer function that describes mu. This is purely based on the frequency domain data. Right? So there's no assumption that for a nonlinear system, transfer function doesn't even exist. Okay? So that's what happened from this branch. You know, after you took it, you don't even know what's in there. You don't even remember. Nothing comes back. It's like a black hole, right? Just get back to the teacher, right? Well, loop shaping did come back to math. So I'll give you credit for that, right?
You're lucky sometimes.
No, it's more than lucky, right? So it become a gold standard in control, in feedback control, right? But still, it's a feedback theory, not control theory. It's a theory they took from a feedback. Huh? And the problem is very, very different. The nature of the problem is very different. This is a very high gain. This is very low gain. So you throw away some gain. You know, that's the cost of doing business. And then you achieve more higher degree of stability. This is not high gain. Our system is not high gain. We don't have anything to throw away. Right? So these geniuses with a PhD in mathematics will tell you, let's make this infinite gain. Let's make controller the sliding mode control, make it very high gain. I went to a conference, I couldn't believe my eye. The guy went up and said high gain feedback. The principle of high gain feedback. If you can use high gain, this is not just high gain, infinite. Okay? To achieve what we're talking about. But it doesn't conform to physical reality. This is what Gunter Stein is talking about. Every component in your loop, be it actuator or sensor, have a bandwidth limitation. Not only the gain, but also the bandwidth are limited. You have to respect it. So the guy who did all that does not respect the physical limitation of the control system, and therefore they don't go anywhere. And people are still doing PIDs, even 70 years later, right? So that's one path. Right? This is the other one. Right? This one didn't share feather. This is even worse. This one doesn't even have the inside of a body and necklace. Right? This went a long way because the civil engineer borrowed the inside from body and necklace. We were able to understand the instability of the loop when you push the servo to the extreme, and they were able to devise ways of countering the servo limitation. That's how they make the gun movement much faster, and they use motors. It was a plain laboratory engineer got an idea. Why don't we use electric motor as opposed to hydraulics in the early days? So it was a great achievement. It was the merging of two distinct engineering disciplines, and they got the job done. Okay. Is that clock right? All right, let's take a 5-minute break. E is mostly 0. There's no direct path. That's your closed loop system, right? So what's the difference between open loop and closed loop? Why do we do it? Because we want to make the system lower or faster as we wish, right? This gives us the means of assigning eigenvalues. Remember that word, eigenvalues? Yes. Okay, so this gives us the ability to change it to what we want, assuming we know what we want. Okay? And this assumes OX are measured, right? Which is also impossible, right? You don't want to measure every state. Not only you assume you know ABCD, you system linear time random with all that assumption, but in addition to this, that's the only require measurement of output. This one you'll require measurement of all states, all process variables. They didn't tell you that, right? They didn't tell you you need more sensors. But they give them credit, and this is very, very useful later on. State observer. And state observer is algorithm. Okay? So you build a you build a state observer. Right? You send the input U and Y to your state observer, and you get xx. And xx converges to x. Xx is a approximation of the x. Okay? Then you can replace this to k x back. Then you don't have to measure everything. Okay? So the state observer is the information extractor. It takes the variable, it takes the available signal U and Y and obtains all state variables information. That turned out to be a ingenious mathematical maneuver. So that's why I say this is useful if you know how to use it. Okay? So that's what you need to know about state space. Yeah.
Can I ask you, and perhaps it was taught in linear systems, and perhaps I don't remember, but pretty much every time we do like this, and we assume that D is usually 0. I think in my class we knew the form, but I hardly ever used D. Isn't that also an assumption, and why is it that we assume that?
Mathematically, you don't have to make that assumption, but in reality, what is D? D is there's no delay. Immediately, you change the A, you change U, Y immediately changes. So that's a instantaneous change, and that normally doesn't matter. Like a motor, you provide it with a current. The current drives the torque. Torque changes acceleration. But between acceleration and the displacement, there's still 180 degrees phase lag. So do not see that instantaneous change. This is why D equals 0 in most of the cases. Okay? Of course, they don't explain it. Okay, so that's roughly in 5 minutes what you learn in linear system. And of course, the concept of controllability of observability is all mathematical concepts. Okay? But then we ask ourselves, another what if we operate under another paradigm, another narrative, another set of assumptions? What if we don't make this jump? Very questionable jump. Huh? What if we make a more realistic assumption about what we're dealing with? Isn't this too idealized? You assume away the most of the difficulty in your problem, the difficulty of dealing with disturbance, the difficulty dealing with the changes in dynamics. Those are the very reason you see that. If you don't have those, why do you use feedback? You can use open loop. Okay? So this is what the Chen question in 1954, but he didn't give answer. Okay? And this is ADRC. So somebody came along in late 80s, early 90s, say, this is nuts. Let's do it differently. Let's do it, let's solve a real world problem, not imagined one. Right? So, so that call it a different paradigm, a different set of assumption, different, it's a different system of understanding. We call it narrative. And you create something in parallel to to 440 to linear system. And say we don't have necessarily follow your logic here, because we think we're wrong. We think this is unreasonable. We think that this is excessive. Right? We keep your mathematics. We keep your the hard-earned understandings of Boolean macros and hard-earned understanding and skills from state observer, but we're going to do something different. Okay? So what is a reasonable assumption, but still give us the opening to solve the problem? Yeah? It's not, if it's completely unknown, then just think PID. Okay? Think PID, you don't need to know any information. Okay? But if we take like a halfway between this and this, what is halfway between this and this? We think maybe this is way to do it. We think maybe physically, we assume that the acceleration of this mass is partially known. It's partially known. At least we know this part. See, this is the acceleration, right? Acceleration we assume has two parts. This is the part we have good control. This is the part that we may not have good control. We may not even know. Right? Now, if somehow, based on the state observer concept, we can extract this information and use U to cancel it. Okay? If somehow we can do this, if somehow we can estimate unknown part and cancel it out with control action, then before we design the controllers, we first reduce the plan to a double integral plan. So if we write it in Simulink, this is what it looks like. Double integral, right? So this is y. This is y dot. This is y double dot. Y double dot equals u0. U0 is something we can change. Okay. And y double dot equals u0, and u0 equals, we can do a kp r minus y plus kb r dot minus y dot. Okay? This is our final goal. We make y follow r by making y double dot equals that. This is this is the PID design principle, although never explained that way. What is PID? What is the principle? What is principle of design in PID? We all tune the numbers. What is the principle? The principle is make y double dot like this, and when you put it in this form, y necessarily y will follow r. If not exactly equal. You want y follow r, right? And that's the design principle to make it happen. You need to make y double dot, you need to make acceleration follow that pattern. When you make acceleration follow that pattern, you're in business. You're good. Okay? So this is the light at the end of the tunnel. We're not there yet. We're saying if we can do this, double dot. If we can do this, then just make U0 equals this, then we're done. We're done. Huh? So now we have the problem reduced to this. We still have made assumption that this is two part. You know, this part, that part is known, this part is unknown. We still have to figure out a way to estimate. So for this to happen, U equals minus F hat plus U0. Okay? And this will make y double dot equals this, and that will so I go to the end form and we work our way back. So that will be our control law, if we can do that. And this will solve the problem. And you can, I'm going to assign you, I'm going to ask you to do a design project, right? You can try this out. You can try this out and then see if it works. So everything is straightforward. If somehow we can do this, right? If somehow we can get this piece of information, the estimation of f in real time. Do you still follow me? I haven't given you the most important part yet, how to find f hat. But if I would be able to do it, this would naturally follow, right? There's no difficulty in understanding of this, right? Yes. So we reduce the amount of the amount of assumptions we make. We only say this has two parts. One part is unknown, one part is known. Right? And if that's the assumption that we go with, it's still assumption, but it's much more relaxed. Right? All we need to do is figure out this part. F hat. And F hat is all of a sudden become feasible because of this. Because of the state observer. State observer was developed under the strict assumption of A, B, C, D are given. Okay? But we repurposed it. And this is the most brilliant part of the FDP-driven detection control. Okay? Of this paradigm, of new paradigm. We repurpose something there from the linear system, and we creatively get this piece of information. How? And you experimented with it. Right? You did do some simulations, and Gianfranco, years ago, your group was also working on it. Right? This time, make it land on a real hard problem, solve it. This time, you make it solve hard. Make somebody come to your lab or come to see your explanation and shake their hand. This is not possible. It happened. One of my students went for Lincoln Electric, and he shows his senior colleague what he did with ADRC or what we did in ADRC. You couldn't take it. This is not possible. That has to be a fake. Because we are in a different paradigm. We're in a different dimension. The engineers who tune PID mostly never get to know how to do this. State observer. The mathematicians, the graduate students who can do this, never in their life imagine they can do this. So get two sides never be able to couple with each other until somebody cross that bridge. And this symbol is the guy who invented the extended state observer. Something this important, it does have a distinct name, right? And the name is ESO. Extended state observer. I have such a big board, I'm running out of place. I'm right on time. I still have that's why I had to cut it short.
I'm sorry.
That's why I had to cut it short.
Oh,
Okay, I want to keep a few minutes at the end.
Oh, no, of course, please.
Yeah, so don't do that. But it's good. Of course, you're always welcome to the channel. But that's one last piece I covered today. How do you do this? Even the brightest mind in the field, the guy who dominated the field for 30, 40 years, they have to come around and they have to study extended state observer. They have to reference this paper from 1995 in a different language. Yeah? So I believe this is a watershed moment. That you move from one paradigm to another, and this allows it to happen. It's not just empty talk. We're not studying philosophy here, right? But philosophical inquisition must take place because without questioning what has been done, the assumptions have been made, this wouldn't make sense. If I come out straight, talk to you, give you this, you wouldn't say, what? Why? I'm fine with my linear system. I got an A in it. So let's see. How do we bring this into the picture? Okay. We have a system like this. We have a second order system, x1, x2. Right? So x1 dot equals x2. That's one way to select. And x1 dot is y, right? Y equals x1. X1 dot equals x2 dot. This is y double dot. Okay. This is y double dot. What is y double dot? Well, y double dot equals f plus bu. Okay. That will be end of story if we use linear system, but it is not end of story here, because we want to estimate f, and because we can only estimate the state if f is a state vector. It's in the state vector. So we must bring f into the state vector. So therefore, we define x3 this is the key. We make f3 a state vector, a state. So we have a second order system, but third order state space equation. This is the third order, right? The last equation, you say it doesn't make any sense. You take the differentiation of f equals f dot equals h. You don't even know what it is. That's fine. Okay? But then you do this. then you write it, this is your state vector, your state observer now. And I'll explain this. So you replace this with F3 hat. I'm gonna stop you now because I ran out of space. So this is something you can implement in Simulink. This is U, this is Y, and this X hat, and this is the state observer. Right? You put this in state space, it gives X hat. X hat has if you use D max, you can have three variables, X1, X2, X3, and this equals F hat. So the third state variable out of your state observer is what you're looking for in your control law, and that will do this magic. That will allow this to happen. That's when you solve your problem. And this will be discussed again later. But this is the diagram. This is the illustration of the idea of another paradigm, another way of doing things, another way of thinking through the problem. I'll pause here for you to take it in to digest it, to maybe ask some questions. And we still have a few minutes left. And then I'll discuss the next small trick, which earned us 7 patents. But right now, conceptually, this is all you need to know. Okay, this relieves you of all these assumptions you saw in 440 and in section. Okay? You break cycle. You break the cycle in all those classes. And if you want to know how mathematics works, this is how mathematics works. Matt, you saw it a second time. What do you think? You got it now? Put you on the spot, right? So this is a critical moment that we take F as a state. Nobody does that. But it makes sense, doesn't it? If you look at this expression, this information is all there, hidden in U and hidden in Y. Right? If you look at this and say, if somehow I can take the approximate the double differentiation, and if I differentiate Y twice, right, and I subtract from Y BU, which something we know, don't we get F? So So the information of the this unknown part in your acceleration is hidden in these two signals. In these two signals, the observer is help you to bring it out. Okay. If you go straight to take second order differentiations, you run into all kind of noise problem. Physically, it's difficult to do, although it's not impossible. So there are people who were doing this without using the observer concept. They were just trying clever ways of taking differentiation twice. If you have a Rockwell motor, an encoder, and the encoder is very clean, right? No problem. Take the encoder output differentiation twice, or differentiate it twice, and run it through a low-pass filter. It's useful. Right? So you don't have to do this. And a few days ago, a few weeks ago, one of my friends took his son from Texas to come here to see me. Right? He was designing an electric silver board. Right? And his control system gets way out of hand. And so he did something like this. In his silver board, the model, he calculated this. And inside the diagram of the controller. And he subtract this, he subtract this in the U signal, and approximately make system like this, and he's the one-lap tuning diagram from this much to this much. Greatly simplified. This is a high school student. And through his father, I know his father for many years. His father introduced this to him, and he was able to decode what I just talked about in class. But he didn't use observer. He just physically, based on his physical understanding, he was able to extract the information he needs and subtract it in the signal, control signal, and greatly simplify his plan. This is all about simplification of plan. Before you design controls, this is where you design control, right? Before you design control, you make little adjustment to your plan, right? And thereby greatly simplify it. So we always think about in linear system, let's deal with A. Let's deal with B. Whatever given, let's model it. Then design control. In this paradigm, in this narrative, under this set of assumptions, we said no. When we design controller, we design controller for ideal plan. This is the ideal plan. The A for this is 0, 1, 0, 0. Right? That's A. So I always design controller based on ideal plan. And if the actual system is not ideal, make it ideal. Find out whatever deviation, the dynamic deviation of the plan from the ideal one, and make correction. So you don't redo your control design, you remake your plan. Does that make sense?
I think after I watch this another couple times, it will begin to. It is certainly different.
Every time I explain that, I explain in different way. It seems like I couldn't stand saying the same thing over and over again. I couldn't stand it second time. So when I watched, what's his name? The guy who wrote the biography on the Wright Brothers. David
McCullough?
McCullough, yeah. The first time I watched the video, it's just shocking to me. It's just so refreshing. The second time I saw him on a different show, You said exactly the same thing. No new information, and maybe it's different. Maybe I don't know this good enough. So every time I try to explain it, I try to explain it in a different way. You know, my interpretation. I always try to improve on my delivery. Right? So people say every time you explain it, you explain it differently. Maybe it's me. So, but I will give you my 2003 paper, ACC paper, where I made the final took the final step, because in here, yeah, how do you design your case? How do you design your state feedback? Right? You always assume a given set of eigenvalues, then you find the K. But who gave you eigenvalues? Nobody gave me eigenvalues, so I give it myself. Okay, I said, put all this multiple poles, multiple eigenvalue L to the C. Right? Then there's only one tuning parameter in K. Right? So in this case, this will be omega C squared, this will be 2 omega C. If I put both poles at omega C. Then I have only one parameter to deal with when I tune the control, high, low. Okay? And that's 2003 ACC paper. Same thing with this. This is I put all the eigenvalues in the observer at omega O, the observer bandwidth. Then I'm left with only one tuning parameters in L. So now all of a sudden I go from 5, 10 different parameters to 2, omega C and omega O. Both make sense. Omega O tells me how fast my observer is. Omega C is how fast my control system is. And I always have to play within the rules. I always have to respect the boundaries, like what Gunter Stein was saying. So the bandwidth, available bandwidth, that concept can help me determine the range of omega O and the range of omega C. I will give you the simulation diagram. You have it, right? That reproduce this graph in this ACC paper. And you go from there, you play with it. And you will find that your system is completely, within a range, completely immune to changes in F. Right? Which means, this is part of the F. You can design a control system where this A1, A2 changes from 0 to 100. It still remain the same. Which is absolutely impossible with what you learn here or here. It just breaks the glass. Absolutely. Okay? And when we perform frequency domain analysis on this is time domain technique, right? That's all done in time domain. All of a sudden, in the frequency domain, it has this shape, has this peak, and crossover. And this frequency and this peak doesn't change when A1 goes from 0 to 100. Imagine it. When the parameter changes from 0 to 100, this doesn't change, this doesn't change. Tell me how to do that. Tell me how to do that with given A1. It's going to take me hours to design something like this. Well, if A1 changes, you have to redesign it, right? But here I am. I'm giving you an algorithm that for A1 from 0 to 100, it doesn't change. The property of closure doesn't change. The bandwidth doesn't change. The stability margin doesn't change. That's a dream, right? Yeah. And that dream came true. In a different paradigm, different narrative, under a different set of assumptions. Okay, I'll put it on the blackboard today, so you can test it over the weekend, and then maybe you can redo the design. There were 7 examples on this website, right? You can redo the design using this and make a comparison when the parameter of the system changes. And you make a comparison whether or not we can just perform the same when large variation occurs in parameters, or when you have disturbances. Okay? We are out of time.